Hello, welcome to Disruptive, the podcast from Harvard's Wyss Institute for Biologically Inspired Engineering. I'm your host, Terrence McNally. The mission of the Wyss Institute is to transform healthcare, industry, and the environment by emulating the way nature builds. Our bodies and all living systems accomplish tasks far more sophisticated and dynamic than anything yet designed by humans. By emulating nature's principles for self-organizing and self-regulating, Wyss researchers develop innovative engineering solutions for healthcare, energy, architecture, robotics, and manufacturing. They focus on technology development and its translation into products and therapies that will have an impact on the world in which we live. At the Wyss, folks are not interested in making incremental improvements to existing materials and devices, but in shifting paradigms. In this episode of Disruptive, we will explore bio-inspired robotics. Many of the most advanced robots in use today are still far less sophisticated than ants that self-organize to build an anthill, or termites that work together to build impressive, massive mounds in Africa. From insects in your backyard, to creatures in the sea, to what you see when you look in the mirror, engineers and scientists at Wyss are drawing inspiration to design a whole new class of smart robotic devices. We're going to explore this exciting territory in a 3-part episode of Disruptive, featuring 3 members of the Wyss faculty, CONOR WALSH, Robert Wood, and RADHIKA NAGPAL. Today's guest, RADHIKA NAGPAL, is the Fred Kavli Professor of Computer Science at the Harvard John A. Paulson School of Engineering and Applied Sciences, and bio-inspired robotics platform co-leader and a core faculty member at the Wyss Institute. Naming her one of the 10 scientists and engineers who made a difference in 2014, Nature magazine wrote that her self-organizing swarm robotics are today's state-of-the-art in collective artificial intelligence. RADHIKA is developing programming paradigms that enable new types of autonomous robotic systems to mimic the collective behaviors of living creatures to meet real-world challenges. Inspired by social insects and multicellular systems, she's developing sensor networks that monitor the environment and robots that collectively construct or self-assemble complex structures without human supervision. Her recent work includes the Termes robots for collective construction of 3D structures and the KILOBOT 1,000 robot swarm. Welcome, RADHIKA NAGPAL, to Disruptive.
Hi, thank you for having me.
In order for listeners to get a sense of you as a person, beyond your work and your ideas, RADHIKA, can you take us back and tell us a bit about your path?
Well, I grew up in a small town in India called Amritsar, and I think my life's goal was to leave a small town and enter a big one. And I think a lot of my path has been focused not really with a plan, but just sort of enjoying the opportunities that came along. So one of my first great opportunities was to come to MIT as an undergraduate. And I experienced for the first time computer science and fell in love with the subject. I fell in love with programming. Of course, I fell in love with a lot of subjects, so it was kind of hard to choose. But maybe ironically, the subject I disliked the most was biology. And so I proceeded through life thinking I would be a hardcore computer scientist. And I didn't like hardware or mechanical engineering, and I didn't like biology, and now I do bio-inspired robotics. So I think a lot of times paths don't quite go the way you start them.
I've interviewed people for years, and in almost all cases, people who end up achieving something of significance, it's been this accident, this twist, this turn that ended up leading them there.
Absolutely. I think it makes you more appreciative of all the accidents and oopses and sort of things that people label sometimes as failures actually turn out to be the turning points that lead to future successes. So it's good to keep that in mind sometimes when things aren't going well, that maybe this is the learning point that will make something really amazing happen. When I was starting graduate school, I was really interested in networking and computers and distributed computers. And at the time, there was a new project called amorphous computing. And the idea was that one day we would make computers the way biology makes cells. You just make so many cells, and together they would accomplish amazing things. But the cells themselves would seem really, really limited and small and replicable compared to, say, the whole system, which had millions of cells or 1,000,000 and 1,000 of cells, but you would never sort of babysit or worry about individual cells. So somehow you would get this amazing collective power from a system that was really sort of disorganized in a way, had many individual parts that seemed very simple and unreliable, but as a group would have this power. And that was a powerful idea. There were a lot of fields that were born around the same time. Sensor networks, Synthetic biology actually was also an outcome of that same project area. And a bunch of us got excited about this idea that biology crossed computer science or physics crossed computer science. And at that point, I started reading about biology. And it's funny how, later in life you read these things and they're so much more exciting than I remember them being. And I read about the development of the fruit fly, how cells cooperate to make these exquisite structures. And then later on, I realized that, of course, ants cooperate to make exquisite structures. And there are all these examples where each individual seems so limited, but what they can do together is this incredible, complex global phenomenon. And that just got me very, very excited about what kind of programming goes into that system. If you thought of those systems as having behavior, as running algorithms, what algorithm makes that possible? And I think that's really the path that took me first to thinking about the algorithms and then eventually to building the robots.
It is interesting, the twists and turns. At what point in there, and you sort of began to talk about it, does it shift for you from computer science, algorithms, computation, to envisioning creating the organisms or engines, as you will, that will put that stuff to work?
That was an interesting path, too, because actually for me, that path started after or during the time when I was a junior faculty member. So I hadn't really thought that I would start out and have a lab and do work. I had friends who built hardware, and I thought I'll collaborate with them. I had friends who looked at programming cells, so the beginnings of synthetic biology, and I thought I'd collaborate with them. But I think after a while, you realize that there's a very deep connection between the body and the mind. And it's really hard to separate those two together. Actually, when you separate those two apart from each other, you lose a very deep connection between the fact that sometimes we think with our hands or we think with our senses. We don't think with our brain. And that idea that your body can do part of the computation for you is very, very powerful. And there are a lot of people who understand this. But our understanding has to translate into engineering. And so at that time, I started to realize that I really wanted to build, I really wanted to have tangible examples so that I could make the computation simpler by choosing the right mechanical structures in the way that ants have or termites have or birds have, any of the biological systems. There's a lot of computation that's happening because of the way their body is shaped. And so I wanted to learn more about that, which sort of took me more into mechanical engineering. But robotics is a very interdisciplinary field. You cross all the way from looking at how this is accomplished in biology and whether it's the brain or the body or the colony that's actually achieving the right behavior, or is it, the other end, which is how do we replicate or build those systems with the kind of principles that we have in mechanical engineering where we can't use tissues or cells, but we can use compliance and we can use ideas like simple sensing feedback loops. I think that's what really, for me, moved me past the idea that computation was the only piece that was interesting in a system. It's really the whole system.
Well, it sounds like what you ended up saying was computation takes place throughout the system or throughout the organism, and suddenly you can't just tinker with what might be the brain piece.
Exactly. And so if you think of computation happening in the body, so for example, maybe the way I walk is made better by the fact that my feet are shaped a certain way. So I can walk up slopes or my body automatically balances to certain things. Then my body is doing a computation that's helping with a task. If you go to all the way to the highest level, a group can do things that an individual can't do, or a group can figure out and sample the environment in a way the individual can't. And so now the brain is really the colony. No individual in the colony actually has the full picture. The full picture is sort of distributed over these many, many, many minds. So at every level, there's a kind of computation happening. And it's interesting to understand, how do we take advantage of each of those pieces? And in my case, I am really interested also in that top level. How do you get the most bang for the buck from numbers? Okay? And as a result, be able to reduce the capabilities of the individual to the point where they're really like ants, so that your investment in the individual is small and your investment in making many of them is large. And it's really that distributed group that's going to be the one that solves the problem. It's not the individual who has the capabilities that are so amazing.
Wow. We're going to return to that. But before we do, I want to talk a little bit more about you and your approach. And in July 2013, you published an essay-length blog post on the site of Scientific American title was The Awesomest 7-Year Postdoc, or How I Learned to Stop Worrying and Love the Tenure Track Faculty Life. Now, to honor what you talk about in there, which is your commitment to balance, or as you put it, to a whole life, we'd be remiss if we didn't talk about that, if all we talked about was work. So can you share with listeners a sense of what you wrote there and how you evolved your approach?
Yeah, absolutely. You know, everybody's career has sort of different paths. But very early on, I figured out that as a woman, people really had a very rigid view of what my path could be. A rigid view of how things were done and the fact that as a woman I wouldn't be able to do them. And that was really, I think, very difficult for me to accept. On the other hand, not accepting it meant I got a little used to rebelling. So by the time, you know, I became a junior faculty member, I was pretty used to being a rebellious woman. And I found that often, you know, there's this notion that you have to work amazing hours, you have to sacrifice, you know, everything in your life, and that's what's going to mean you're dedicated. And that's a really difficult way to start your life, you know, to think that everything else is supposed to be less than. And if everyone else in your life isn't ready to be less than, then somehow you're a failure at your chosen path. And I think that message is promoted in way too many ways. And of course, I started in 2004 when Larry Summers gave his famous speech. So, you know, for me, that was upright in front when I started. So my article really was about, you know, if you don't believe that, then what do you believe? What can you believe that makes you go through life? And I actually believe that the best scientists are the ones who have whole lives, who aren't being a scientist to the exclusion of being a good citizen, being a mindful person, being a thoughtful person. And the truth is, if you're running all the time, you definitely don't have time for thought. So how do you create that system where first you believe that that's true? You believe that by creating balance in your life, you're actually creating better science. And then the question is, how do you practically do it? And so it took me a lot of trial and error on the practice part. I think I believed it somehow in the beginning, but it took just a lot of work to figure out how to practically work in a system that was not encouraging that behavior at all. And so different points during my career, I talked to people about my strategies. And, you know, I wasn't very shy about it. I didn't advertise it openly, but a lot of people I know knew everything in that article. And they were often shocked. And they said, oh, you know, I don't think people know this can be done. I don't believe you can do this, you know. And it's like, are you sure? Would you ever say this out loud? And this went on for a while. And then I got really upset. I thought, you know, this is ridiculous, you know. How can people go with these false views of life? So I guess my article was kind of an attempt also to come clean. I didn't want people to think that I was willing to be that person. Even with tenure, I'm not willing to be that person. So I wanted to come clean, and I wanted to sort of put it out there that I don't believe that a system that encourages people to give it all up in the name of science is a good system.
I remember the line that struck me the most in there. So you're writing to the public, and you say in that article, if a department or a university decides that I'm not giving that percent of my life to them that works for them, well, I guess I'll go somewhere else. And if a marriage partner felt that I wasn't giving, I mean, it seems like you're really willing to say that the whole may not fit with people, and you've got to find people that it fits with.
Yeah, and it's interesting. Like, you'd be surprised. I got so much email afterwards. And to each person, there was a different part of the article that just spoke to them. Mm-hmm. And that, to me, you know, people reflecting back to me what I said has been hugely beneficial to me. I mean, it's made me much stronger and much more committed to thinking openly about these issues, and also just understanding the issues from other perspectives. So that is one example. And I think that what I was trying to hit is that all of us fear failure, right? We fear failure in a big way. And in society, we set up certain things to be all or nothing. Marriage is one of them. It's like divorce is like, oh my God, you know, marriage is supposed to be for forever, and tenure is supposed to be for forever. And I thought, wow, this is really setting you up, right? Because now you look at that and the fear that something that's going to be for forever doesn't happen to you, and you're devastated. So how do you attack that? Well, First is to realize nothing is forever, And I've decided that actually the stupid thing is that, you can quit a job and you can quit a marriage. And to me, quitting a marriage was very important. I saw a lot of women in my family suffer because divorce wasn't allowed. So as far as I was concerned, divorce is one of the best things that, comes with it. But the flip side is the other person can divorce you too. So I figured, I can leave Harvard and Harvard can choose not to tenure me. And that is an acceptable choice versus being an indentured slave. On the other hand, I realized that having kids is the one decision that doesn't come with that. So once you've had kids, there is no quitting.
That is forever.
That is forever. And so I think actually that's the decision people should really be thinking hard about. And that's the one that should invoke fear. I think it's good to remember that there's just lots of paths through life. And most of us don't know what our alternate paths would have looked like. We don't know that we would have been unhappier somewhere else. So, if you just don't expect everything to be for forever, it just reduces the bar, right? I'm not failing forever.
Yeah.
And for me, that's what I was trying to convey is that, yes, I do fear failure. But, that's just how it is. There is the possibility I fail, and there's no way around that. So let's just go with it.
But it sounds like you wanted to set the terms of what failure for you was. And
yes.
Failure for you was failing to demand and at least the possibility of a whole life.
I agree. I mean, for me, it was very much, I had written on my desk, it's like, if I succeed, it will be on my own terms. And that was sort of pasted on my desk for most of the 7 years so that every day I could read it and remember it. And I realized, of course, towards the end, I realized that there is some, I still want success. I still wanted to get all the things I want. But I've seen a lot of people live really great lives after what would seem like really traumatic events. And so I personally believe in sort of, I don't know if restoration is the right word or recovery or rejuvenation, that people can recover from amazingly difficult things. And tenure is just not one of them. It's really, I have a cousin who lost a child.
Yeah.
I mean, can you imagine? That chokes me up. It happened some 20 years ago, and it still chokes me up because I got to watch part of it. Compared to that, I'm sorry, you got to really scare me, So I feel like, my terms, I do believe that my terms are better than what other people were promoting.
And it would be stupidly hypothetical for me to ask if you believe you would be as successful in robotics if you had not taken certain actions toward living that whole life years ago. But can you at least talk about how you think, for you, the two sides, the strong approach to work and the strong approach to life, have fed each other or not?
I think there are lots of ways to look at that. I mean, first, it's really hard to dissect your own life. I know certain things about myself. When I get unhappy, I quit. So that's not a good way to succeed generally, right? Is that if you get pushed to the corner, you quit. So a lot of my strategy is around keeping a big distance from the quitting point so that I'm still thinking well about myself and living a full life where there are many things in my life that are important, many things on which I'm making progress. That is one way of keeping yourself away from quitting. Not all of your self-esteem is invested in one thing. And I think this works within research too, right? We try to do different projects, we teach and we do research, we mentor our students. You always try to remember that there are many ways in which your life is valuable. And therefore, when one thing doesn't go the way you planned, rather than get too hung up, you try to fix it, you try to understand it, you try to learn from it. You don't sit there and label it as a failure and, cause yourself to go down some downward spiral. Because anyways, I think, as my advisor so wisely said, we spend way too much time labeling everything as success or failure. Mm-hmm. And if we just stopped doing that all the time, we would actually be happier people. So part of, I think it's that the ability to have many ways in which I felt my life was valuable has made me more risk tolerant in research, I think. I know that I'm doing something because I'm passionate about it and I'm excited about it and it's risky and it may not work. And I do have an obligation to protect my students. So that's where it becomes a little harder to take risk. But personally, I am okay with who I am and therefore I can take that risk. And so I do think that in a way I've done a lot of risky projects that maybe other people are not so comfortable with. And in many cases, so many cases it's paid off. And so I find it hard to go back and think that that wasn't the right thing to do. Like, I've always worked a little bit in biology, which is not easy if you're a computer scientist, because how do the computer scientists evaluate your impact in biology? It's also not easy for the biologists because you only spend a tiny amount of time in biology. So people said, oh, that's too risky to do. But every time I've worked with biologists on biological questions, it's fed back into how I think about robotics. Even more direct things like how do cells solve problems? How do insects solve problems? How does that give us new algorithms? That's definitely true. But also, how do you think about an experiment? How do you think about a question, an experimental question in biology and computer science? What is enough proof that something is happening a particular way? We rewrite programs in computer science, but when you run a robot, there is a lot of other things happening, and it's interacting with the world, and it's sensing. You don't know all the things that are happening. So you're going to run experiments to try and understand why things are happening a certain way. And in that sense, we're basically replicating exactly what the biologists taught me. So there's so many ways I feel the different things you do feed into each other, and it's very hard to separate them out. But I think also that cross-disciplinary stuff is, helps in many ways. Another sort of example is, my kids will come and ask things about what I do, and I'll go to the Cambridge Science Festival and explain to people what I do. As I'm doing that, the things that people say back to me give me so many ideas, so many ways in which they view my work that's different from an academic who would view a work, or another professor or another graduate student. They really look at it differently. And sometimes those conversations have led me to work on different topics. So I like to have a diverse experience in life. I think it makes for more interesting science.
You've made very clear in that article how protective you are of your time and your commitments. Are you still functioning as an advisor to Harvard Wyss, Women in Computer Science, and what does that mean to you?
Yeah, well, that is one of the highlights of my last many years. So the Women in Computer Science group started with a very small number. Actually, it started and restarted many different times, but never took off. And then about 4 years back or so, it started with a small group. And today, there's about 300 members on the mailing list, and we talk about articles on the mailing list. They host a whole conference where students from the New England area come to Harvard for a day of events and hackathons. It's an amazing experience. And I have to say, there are a lot of times I feel very depressed about the situation for women in academia and the sexism that seems to persist. And it's really the young people who keep me going. So the Harvard Wyss, I tell them, it's not me who is their advisor. Uh-huh. They are actually my advisors because they're telling me how things are going to change. They're committed to changing. And with that group, I feel much more optimistic about the future. I feel that these women will go out and demand that people meet their terms. And they're not shy about it, and they understand a little bit better that, everybody has pluses and minuses, and it's not okay to target them as with only minuses because they're female. But it's also not okay to assume that, you know everything because you're in computer science. And I love the fact that they really deeply think about the articles and that come out and the things that happen, and they give me a chance to talk to a lot more people about how something affected them or feels. I used to feel very alone, when some event happened. Most of the men around me don't want to talk about it or don't really want to even bring it up. And so you just read something and your heart just shrinks and there's nowhere to go, And now, in an interesting way, I can talk to the Harvard Women in Computer Science. I think at the beginning I felt very alone. So a lot of the Harvard women are my advisors.
We're going to shift into the work now. This is a question about how you integrate the biology and the computer science. I've read that a couple of your team on the Termes project, Harvard graduate student Kirsten Peterson, staff scientist Justin Werfel, actually spent time in Namibia observing and studying termite mounds. Have you actually gone to any of that type of biological observation?
Yes, I got to go to Namibia too.
Ah.
I think part of this was a deep envy that I have been building up over a long time of the fact that biologists get to go to all these amazing places and I only get to read papers. So the Namibia trip was our first example. Actually, the termites are a classic system where people have studied decentralized cooperation or implicit cooperation. So the idea is that termites don't necessarily, I mean, there's definitely no supervisor who's telling them what to do, but there isn't even some sort of hierarchy. Instead, there's sort of these chance encounters you could think of where information is propagating, but there's also just encounters with the environment. So imagine if people together were building a puzzle. You don't necessarily need to talk. You can sort of see what other people are doing. You can see the puzzle pieces that have been placed in the past, and you can sort of infer from past actions from the environment what past actions have happened. So people believe very strongly that termites are one of the sort of key examples where this is true.
Can you talk a bit about three big terms here that come into play in a lot of your work? Self-organization, self-assembly, distributed systems. What do those terms mean to a listener or a layman, and examples and the role they play in your work?
So I think that the distributed systems is a good place to start. So, and it's really easy often to understand these systems if you forget about termites and just think about us, a group of people. So if you have a group of 5 people doing something, it's really easy to get together and for everybody to be in the same place and sort of discuss things. Maybe as you get a larger group, you can have cell phones or something. But now if you imagine 100 people trying to do something together, it's not really possible for me to know what the other 99 are doing, and they're distributed over space. So they're in different locations, they're seeing different things, they're moving at different rates. And the flow of information cannot be that I know every millisecond what every millimeter that every one of the 100 people moved. Instead, if you go to the other extreme, maybe I don't really need to know what the individuals are doing. I can just do my bit. And if I know that everybody else does their bit, then we kind of understand that all of these bits will add up together in a good way, that they won't add up together in a bad way. And the field of distributed computing is really about algorithms that function that way. So you can think of computers connected over wires. That's sort of a very traditional system, but the internet, as you can imagine, is a huge distributed system. But in the future, self-driving cars on your road will be an incredibly different distributed system. So all of these systems, each individual can only integrate information that's close to it, but you want the system as a whole to achieve something correct. So in self-organization, it's kind of the same idea, except the assumption is really that the individuals are very much more myopic. So I really don't know. I don't know if there's 100 other computers or 1,000 other computers in my network. I don't know if we're connected in a tree or connected in a flat network. I know very little about the system, and I can operate on very little information, and still the system can achieve what it needs to achieve. So if you think about a distributed system and you say, okay, make each individual in the distributed system simpler and more of them, then you're sort of moving towards the field of studying self-organization.
And self-assembly.
Yeah, so self-assembly is sort of a very specific kind of self-organization. It's also something that isn't usually studied in distributed computing, which is, how do you form structures? And in physics, self-assembly is, how do snowflakes form? Right? That's a good classic example of a really beautiful self-assembly. And the assumption is not that there's a water molecule who knows exactly what shape they want to form, and they collect and talk to the other molecules and tell them exactly where to stand until you get the perfect shape. Instead, somehow there's this process where a structure is able to form, but the individual rules are actually quite simple. They might be rules of just adhesion and repulsion, and somehow the adhesion and repulsion, or the specific way molecules fit together, means that the assembly proceeds in a particular way. So as a distributed system, you could say you just have this bag of stuff and you shake it, and now suddenly, even though each individual part only can interact with things near it, you're supposed to get the end structure that you want. So the field of engineered self-assembly is basically how do we make the molecules or the robots or the cells that self-assemble the thing we want, as opposed to the thing that they're naturally going to do. I'm interested in self-assembly because at one level, you could think of, in the future, creating programmable materials the way we have 3D printers. Imagine materials that could self-assemble into one structure, and then you melt them and self-assemble into another structure. So there's a lot of emphasis on this idea that we could create these kind of active materials that could change shape. And at the other extreme, if you think of robots putting together a house, that's also a form of assembly. The parts of the house are not putting themselves together. They're not smart beams. But actually, the very act is exactly the same. So any kind of assembly process where many individuals are assembling together is essentially a larger version of self-assembly. So I found that that's one of the interesting areas. You have to ask, like, if you're going to make a structure that has something very, very specific at the end, you want to make a fruit fly. How much of the picture of the fruit fly needs to be in an individual cell? That's essentially the question. What's the program that goes in the cell that self-assembles a fruit fly? And I think there's so many people who are fascinated with this question, from within biology to physics to synthetic biology to computer science, there's just so many ways to think about the problem, and I find it really exciting.
In February of 2014, your research group announced TERMES, the creation of a robotic construction crew capable of assembling blocks into 3D structures without any human intervention. No foreman, no central brain. What is the story behind this? What inspired you? And then a little bit of the path. What's a little bit of that story of how you got to that moment?
So I actually started working on this project, I want to say around 2004. And it was really my co-author, or the first author of the paper, Justin Werfel, who came to me with this idea. And his idea was, just in simulation, just in a computer model in mathematics, what would be the program that a termite would run or an ant would run to build a structure that had certain qualities? If I wanted to build a wall, or I wanted to build a particular shape, what would the individual need to know? And how would it happen if they were 10 individuals or 20 individuals? Would it matter? Could it just go faster if you put 20 and slower if you put 10, but that you didn't have to change at all the rules by which anything was being built? And so he was really inspired by all of these papers on termites and wasps and ants and the construction rules that biologists were uncovering. So he got me really excited about the project. And I have to admit, after that, I read a whole bunch of papers because of him. And we started working on it, and we were really surprised. We realized that there were simple ways about thinking about the formation of structures, so that you could actually take a really complicated structure idea and write in computer science what we call a compiler. A compiler is taking one description and transforming it into another. And it has a mapping between one description and the other. So we could write a compiler where you could essentially draw a shape, and out would pop these rules that individual sort of simulated agents could run around and build these structures. And this was super exciting. And this was really Justin Werfel's PhD thesis was about this topic. So the thing, though, was there were so many ways in which we were living in this complete abstract world. And so when I talked to roboticists about this, they sort of just shook their head and they were like, yeah, you're never going to build that. And I had a really great friend, James McClurkin, who won numerous awards. Actually, some of his robots are in several museums. And so he was building robots. He was one of the first people I knew who had a swarm of robots. He would show up with the suitcase, open it up, and his 50 robots would come out. And it was incredible. Nobody had that. And he taught me new ways of thinking about robots. He taught me about, what things are easy and hard, that seem easy in math but would not be easy to build. And I think over time, Justin and I got more and more excited about this idea that we could meld those two ideas, that if we thought harder about a robot that really could be built, then actually we could design algorithms that operated in that model. We didn't have to have algorithms that were not so well correlated with reality. And so that actually led us in this direction. And we did actually a couple of Lego Mindstorm robots. This was actually my start into robotics, was actually using Lego Mindstorms. And then Kirsten joined our group. And so Kirsten actually independently in Denmark had been thinking about the same ideas with her master's thesis. And how would you build robots that could move blocks around and climb over them? So how would you make three-dimensional structures? So just to give you a sense of what's challenging, robots that climb are a cutting area of research. Robots that manipulate are a cutting area of research. Now you're asking a robot to pick up something and climb over the structure previously built while carrying this thing and then place it well. And so you're basically taking the worst of climbing and manipulation and sticking it together. So the question was, is that actually going to make it easier or harder? So your first impression might be that's just taking the worst of both worlds and putting them together. But the flip side is that a lot of times, we build structures, we work with tools, right? We work with tools that fit our hand. We don't work with tools that, only a chimp can use. So, and the chimps use tools that are appropriate for them. Birds use tools that are appropriate for them. So customizing both the material you're manipulating and the robot that's manipulating it turns out to be a very key thing that can be exploited. And that simplicity, like, termites have these very special mouth parts that help them manipulate mud in really well ways. They're not good for manipulating other things. So we built our robots to be really good at manipulating particular kinds of blocks. And we changed our algorithms to think about how we would compensate for the fact that, robots can't build things that will fall over halfway through, or they can't lock themselves into a hole, or they're not going to be able to communicate with other robots that are behind a wall or far away. So can they do it without any communication whatsoever? And so we melded sort of all of these different ideas together. So, Justin's really deep speciality is mathematics and algorithm development and thinking about decentralized systems. And Kirsten is an amazing builder. And I'm just fundamentally sort of interested in implicit coordination and networking. And so the three of us together were just this team where we constantly went through different ideas, and it was a terrific time. So the paper came out in Feb 2014, and we really started the project 4 years earlier. So it was 4 years marathon getting to that point. It was definitely not something that sort of emerged overnight. And there were points in the middle of the 2-year point where I think all of us just thought we were doomed. Like, we were just going to stop at the halfway point and declare victory and say, okay, we learned that this is harder than what we thought, and, this is it. And you do, I think that that's also important, that you have successes and failures. And even our final paper is both, to me, a success and a failure. We thought we would be able to do a much bigger system, and we thought we would be able to do it for longer. But we still have a lot to learn about how to make these robots robust. So, for example, the robots, there are lots of error correction that happens in the system. And we thought about low-level error correction and high-level error correction. But if a robot actually fails on the structure, you need a tow truck, And so it's interesting that, you look at termites and they're able to drag the dead termites out of the way. They just build over them. Like, they have a lot of ways in which they can compensate for the world. And we built these robots and they're super specialized. And thinking about how are we going to have robotic systems where many robots work together? Well, some of them are going to fail. How do we deal with those failures? Which failures require creating essentially an immune system, or basically the second layer of robots that is looking for failures and clearing them up. And I think that's, to me, all of us are really excited about thinking about this, because I think up till now, we just gave up on that part. We're like, okay, that's it. We can't solve this, or oh, there'll be another robot that will come and take it away. And that sounds like a horrible and difficult one, but we're just going to ignore it. But I actually think that what we were learning in that process was we're learning how to build more robust robots. I think that was one sort of lesson. The second, like I said, is the more robots you have, the more failures you will have, even if they're low probability. So how do you deal with rare failures and whether you need an immune system? I think the other thing we learned is that, humans can build in very rigid ways. We build out of bricks and we build out of 2x4s. Insects build out of mud and sticks and much more compliant structures. And as a result, when they're in an environment that doesn't fit their model, they don't need to level the ground in order to get something done. They basically, termites will build totally functioning mounds that lean against a tree. And as far as we know, they're just taking advantage of the tree. They're like, this be part of the wall. We'll just, put it right in this corner. Bees do that. So if we wanted to have robots that were actually in a disaster area or building levees or sort of put in an environment that's unfriendly, we'd really want a system that's more like the insects and less like people, where we need to cut everything to the specification, have a blueprint, clear the ground. And so maybe robots that actually manipulate sandbags is better than ones that manipulate bricks or square objects. So manipulating sort of softer materials might be really interesting. So I think all of the ways in which we didn't achieve our goals, although, we're pretty excited what we did achieve, but all of the ways in which we didn't achieve our goals are actually the starts of really new investigations. Like, well, why did this happen? Why didn't we think of this before? And if we did think this way, how is it going to change our whole thinking about collective construction or our whole thinking about self-assembly? And I think that, to me, is what keeps me going.
And what stage is that work in? In other words, how far have you gotten along producing hardware versus just the theoretical paper?
The paper in Feb 2014 was really about having a combined hardware system. So that's really what took us the 4 years, is building the full hardware system. So we're not working on that particular version of the hardware system anymore. But with a former postdoc of mine, Niels Knapp, who's now a professor himself, we actually started working on robots that deposit foam. So trying to look at robots that were actually manipulating material that's much softer and fuzzier. And basically you could, get yourself out of any system. And also looking at robots that could build structures where you didn't know the end goal ahead of time. So an example would be, let's say you put a robot in a situation and it needs to reach some light or it needs to reach some particular goal. But there's a bunch of rubble in front of it and it can't get over it. Can it build itself out of the situation? And so you don't know exactly what you need to build, but you do know that you need to build some sort of ramp that's basically going to get you there. And obviously, since you can't climb over these rocks, there are things that you can and cannot climb over. So we looked at how we would algorithmically solve that. And I think we have a lot of really interesting answers there. So that project is sort of halfway through, and I'm thinking about how that one is going to morph. And I think Niels is also thinking about how it's going to change. But self-assembling in the face of real uncertainty. I think that's sort of the direction in which we're both trying to build hardware, but also I think where the mathematics gets much more complicated. We're not as good thinking about spatial problems when they're not sort of in a nice gridded world or in a nice sort of rectangular world. That's very comfortable for us in geometry. But thinking about sort of arbitrary functions in the environment is a little bit harder. So there are a lot of, I think, technical reasons why we just, as of yet, don't have as good ideas about how to do it or even how the insects do it. This is also part of the reason the Namibia project is really interesting to me. So we're continuing that project and we're working very closely with biologists to understand how are the insects thinking about building when they don't have a very specific goal in mind, but they have a function in mind. They're either building for shelter or they're building to get out of something or they're building to close something. And they're really just responding directly to the environment to take decisions. I think the more we understand techniques from insects, which are, easier to study than, say, beavers, we have read papers on beavers as well, is just that maybe we'll get more ideas and more ways of thinking about the hardware as well.
Yeah, and we're going to switch now to the swarm, but I wanted to say that if anyone's asking, so what's the practical value of this sort of thing? You referred to it a little bit, that could we build a system of robots that could deal with natural disaster areas or areas of danger to humans, and they could go in and sandbag a levee or do something with something that's happened in an explosion and that sort of thing, right? That's sort of the picture of where that could go.
Absolutely. That's part of it. But also, if you think you want to build underwater, right? Or you want to build
in space, yeah.
In space, or you want to build in the desert, right? Where are the places where we could basically not send people, not have to worry about their lives, instead send a whole bunch of cheap robots and not worry about the cheap robots either, right? If you send a super expensive robot that's doing a terrible job, then you might as well send the people in. But if you're sending a lot of robots that are doing a reasonable job, then they're machines. They're not alive. And so that's a really big difference. I think there's many environments where robots can build small structures to help. Also, just a sort of aside to that is we do need to get better at building robots that do more than observe. And that's part of the goal also, is a robot that just walks around and sees things but can't take any action is still a really pale choice. So how do we get to that point? And I think construction is just one of those examples. What we really want to build is robots that manipulate.
Okay, so let's talk about the other big thing in the last year. In August 2014, your group unveiled your 1,000-robot swarm. Small, simple robots collectively arrange themselves into shapes. Again, no central brain like ants or termites. What is that story?
Swarm robotics is actually a field that has a long history, where long is like a few decades. But, the idea is that, like we were talking about self-organization, the idea is that rather than having the one perfect robot, which anyways is not necessarily very useful because it would be slow, having many, many, many simple robots and using the swarm to achieve things in the way an ant colony achieves things. So if you think about like a bee colony, right, an individual bee is pretty small and puny, and yet, a colony of, say, 10,000 honeybees can forage over areas 2 to 6 kilometers range, right? So you imagine you have this little group of robots that could actually monitor and look through an environment that large, and you weren't worried that, a few of them got stepped on or some of them fell out of the air or a few things happened, because you have 10,000 of them. And so, you're manufacturing more robots quickly. So if you thought of your bee colony as a robot colony, it's an amazingly powerful system. So the question is, how do we get there? So the swarm robotics field has really been looking at, first of all, how would we design colonies of robots that would do something that was useful for us? So monitoring is a great example. Or, foraging, so going and finding things and bringing it back to a particular location. Cleanup, environmental cleanup is another example. All of these are examples where having many simple robots could be extremely useful. But it's been very, very challenging to get there. I think in part because we don't really understand what is a sufficient robot, and also we don't understand what things we're going to face that are going to be different about 100 robots than, say, 10 robots, or different about 1,000 robots than, say, 100 robots. So simultaneous to all of this, there's been some really, really great projects, and we've learned a lot of lessons from them. So in no way do I want to say that, our project somehow was the first in that sense. But our goal was really to try and push it above. There were a lot of groups that got stuck at making like 100 robots. And the question is, are 100 robots like 1,000 robots? And the answer is definitely no. I can conclusively say it's not true.
Yes.
And so the question was, what's going to allow us to get to 1,000 robots, where we really experience our robots the way one thinks about an ant colony, that there's so many of them that you're not going to name them, you're not going to touch individual ones, you're not going to remember the ID number. If one of them moves, you're going to lose track of it. That kind of number, how do we get there? And so I worked together with a really talented person, Mike Rubenstein. And Mike is actually starting a new faculty position soon at Northwestern. He will definitely continue. He has some more crazy, crazy ideas. So his lab's going to be a very, very exciting place to watch. So Mike felt that given the way technology was moving, we really were at the right point where we could imagine not getting stuck at 100 and thinking about what would 1,000 robots look like, and what things would 1,000 robots not have that we were giving to 100 robots but wouldn't be willing to do 1,000 times. And he started with that mentality. So we created it's called the KILOBOT robot, and the idea is that you would buy robots in the kilos. So that's the kilo. So 1,000 robots, you buy a kilo of robots, the way you buy a kilo of bytes. And each robot it's a robot. You can program it. It has a controller. You can tell it what to do. It can talk to its neighbors over a short wireless range. And it can communicate very complicated things with its neighbors. It can give a whole program to its neighbors if it wants. And it can move in a controlled way. And basically, we thought about how to make all of those aspects cheaper, what kinds of technology we could use, how to mass manufacture the robots, how to let them sleep in low power so you would never have to touch them, and all of these factors. And the result is, I have to say, this is one of the projects where I feel we achieved more than we had set out to, which, when it happens, it's such a fabulous feeling. In the process of really trying to make a robot that we could design 1,000 times without making people in the lab super unhappy, we created a robot that was really easy to manufacture. And so midway through our project, thanks to the Wyss Institute, we were able to license our robot to a company, K-Team. K-Team now produces this robot. And at this point, there are about 10 other groups that have hundreds of robots that are the same robot as us. So now we have a community of people with these robots. These are not robots that go on the shelf. These are robots that are being programmed to study collective behavior in so many different ways that I had never imagined. And with the Wyss Institute, we've been able to create a software system and a programming environment. And so now there's biologists using our robots, which I had never imagined would be the case, but they're very excited about them. And there's actually a group, Roderick Gross's group in UK, that has 1,000 robots of their own. So now there's another group that has a swarm as large as ours. And I never imagined that this would be possible. So that actually was one of the earlier and sort of growing outcomes of this, has been that creating these sort of platforms, these robotic swarms, means that more of us can experiment with them and more of us can quickly move the science forward. What is different about algorithms on 1,000 robots? What are the kinds of failure modes or emergent patterns that are going to happen? You set off a chain reaction. What do those chain reactions look like? In 100 robots, first of all, people run very few experiments with 100 robots. In 20 robots, you don't see chain reactions. You don't see rare events happen. In 1,000 robots, you see every rare event happen because 1,000 robots for a long amount of time, you're just playing a probability game. When we started programming these robots, we learned very, very quickly how incorrect our assumptions were, our mathematical models were. And now we're starting to sort of really understand more and more about how to better program these systems to be really resilient.
And just so people get a picture, what you did when I first heard about this story on the news, what you did with those 1,000 robots.
So we wanted to demonstrate that you could program 1,000 robots, which are all super unreliable, not precise, can only talk to their neighbors, that you could program them to do something that was really specific and predictable and much, much larger phenomenon than any individual robot could experience itself. So we chose self-assembly, or we chose shape formation, because that's one that you can really show that somebody can pick an arbitrary thing, and I have a compiler that will put the rules and the robots will actually form it. So we chose particular shapes. We chose the starfish, and in particular, the starfish is actually a model. It's a dream in people who study self-assembly because it's an organism that has incredible powers of regeneration. So if you broke part of it, it should repair. We can't actually do that yet, so we tried to sort of at least create that shape. The letter K, because it's arbitrary. A wrench, thinking that in the future these would be like programmable materials that would actually produce something physical at the end. So those are all fairly arbitrary shapes, and what we wanted to show was that we could actually program 1,000 robots to do something predictable, reliably, even though each individual had a very limited... Each individual robot can actually only see about 20 robots nearby it. And the whole system, you can imagine, from end to end is many, many. The information from one end to another is really, really far.
And you can go to the Wyss Institute website and see video of this, but these 1,024, I believe it was, little bitty robots, each the size of a quarter, each vibrating on the surface, it took them how long to form into the shape of a star?
Long. About 11 hours.
About 11 hours. But they did it.
But they did it. And I think that actually we learned something very specific. First of all, 11 hours of running robots is not a common thing to do. So the way we actually made the system work is we realized that we had to create systems that would look for errors and find errors. So as I was talking about this robot immune system idea, there were so many ways in which one failure from one robot can actually cause a cascade. So we thought a lot about how do we have robots that monitor each other's behaviors, where your neighbors can tell you, for example, I don't think you're quite behaving correctly. Maybe you should reboot yourself. And a robot could respond by actually doing that. And we had to actually program algorithms like that to make the 1,000 robots work for 11 hours. One of the reasons why they're slow is because the vibration motors, which are actually very cheap and really very, very reliable in the sense that, they work out of the box really well, they just are very slow. And so you're giving up speed for other benefits. In real robots, another reason why you're slow is that robots spend a lot of time taking decisions. So if I have to integrate a lot of sensor information before I can take an action, then by definition, I'm wasting time in order to take an action. So one of the things that we are trying to learn is how can we have the robots make simpler decisions or quicker decisions, and think about different ways in which we can do the self-assembly so that the whole process dramatically reduces in size. And I think we have a couple of ideas on how we can dramatically, in the same system with the same speed robots, actually make self-assembly a lot faster by just thinking about the process differently.
Let me just ask you one final question. What's the question or the vision that's turning you on the most right now?
Oh, that's a tough one. And since I have a whole life, you can imagine I have many visions. I just find it amazing that there's so many systems where the collective has so much power than the individual. And I think human systems are like that too. And for me, one of the visions is just really understanding that process. What is it about groups that makes them really strong and really powerful? And in some sense, what is it about groups that make them not that way? I think there are a lot of people who would love to understand that, not just for ant colonies, but also for human colonies. What makes a research team, an institute, function in an amazing collective, where all of us come together and the result is supremely more powerful than any of us could have produced. That kind of power, would be excellent to understand.
You've been listening to Disruptive Bio-Inspired Robotics. I'm Terrence McNally. My guest today has been RADHIKA NAGPAL. We invite you to listen to the other two segments of this episode with Robert Wood and CONOR WALSH. We'll talk with Walsh about his work with soft and wearable robots with practical applications from healthcare to the military. And Wood's projects include tiny flying robo-bees and self-assembling robots inspired by origami and pop-up books. You can find both those podcasts at iTunes or SoundCloud. You can also find them at the Wyss site. Wyss is spelled W-Y-S-S, and the site is wyss.harvard.edu. You can also learn more there about the innovative work of the Institute. There's an extensive library of articles and videos. You can also sign up at Wyss, iTunes, or SoundCloud to have Disruptive podcasts delivered to you monthly. My thanks to Seth Kroll and Mary Tolikas of the Wyss Institute, and to J.C. Swadek in production, and to you, our listeners. This is our second episode of Disruptive, and if you like what you hear, let us know, and feel free to spread the word far and wide. I look forward to being with you again soon.